100%. Screen. Yeah. It's an intern PM.
Now you should be able to use it.
There we go.
Got the recording already?
Yeah. All right, I'm Ethan Pegku and I am the transportation engineer for PMZ Engineering. Today I'm the interim project manager for the day. Lane's taking her FE, so good luck, but I'm up here with the PMZ team. We're gonna talk about our final presentation for the County Road 38 project. A little quick summary is it's located in Elkhart County, Indiana. We were tasked with redesigning the County Road 38 roadway along with the intersection, a design of a stormwater management system, a visitor center with a parking lot, and a wastewater treatment facility. So a quick recap of my scope was I was tasked with redesigning the intersection along with incorporating a multi-use path and center turn lane along the roadway and a path underpass along with a parking lot to accompany the visitor center. So my design criteria mainly use the NDOT design manual and a WB 67 for the NDOT for the Indiana design vehicle. I also use the Elkhart County street standards for the parking lot and roadside ditches, and then the AASHTO Green Book, get those values. And I had a 45 mph design speed. And from the table, just like my max grade and minimum grade are 5% and 0.5%. So my typical section, I have 3 travel lanes that'll be 12 feet wide and 2 shoulders that'll be 10 feet wide with roadside ditches that have a 4-to-1 4 slope and a 24-foot clear zone that includes the ditch or the 4 slope and the shoulder, and a multi-use path on the south side of the roadway. It'll be 10 feet wide with 6-inch concrete. And the cross slopes for the travel lanes will be 2%, while the shoulders will be 4%. And the mainline pavement will include HMA surface, intermediate, and base. So my intersection design includes 4 approach lanes with dedicated right and left turn lanes. And my main objective for this design was to accommodate both pedestrian safety and accessibility with improved traffic flow. So I divided the traffic lanes into streams to improve the flow and added pedestrian crosswalks that will connect each refugee island, and each turn radius will be 125 feet with multi-use path going through the northeast corner through the intersection back out the southeast corner, and also be raised curb islands and pedestrians stand out. And my visitor center parking lot will include 110 spaces. It'll be 9 by 18 feet with per ADA standards 4 accessible handicap spots with 1 van accessible spot. And you can see from the dimensions shown, there's enough room for 2 lanes of travel and some dimensions for the van bays. And and the radiuses are 30 feet. It's really small, but it says it there. And my maintenance of traffic plan will include rerouting eastbound traffic down Road 19 across 40 and back up 15, and then rerouting westbound traffic up 15 across 119, then back down County Road 19. And this is the road closure, and it'll include, or the only vehicles allowed through will be residents and emergency vehicles. And my total construction cost estimate, I use the NDOT unit price summary, and my main line items are concrete, HMA, and the signal setup. But this was made in 2022, so I had to adjust for inflation, like the cost of HMA and concrete went up slightly. And I included a $600,000 miscellaneous charge for like pavement markings, cut and fill, and other line items I couldn't get to. But my total cost came out to be around $2.3 million. And I'm gonna hand it off to Andy.
Thanks, Ethan. As Ethan says, I will introduce the water resource part.
So here is our scope. So we will reduce the solid and the mantle loadings by 60% and all improves the service to infiltrate or filter at least 1.25 inches of runoff. And the design system to control the strong water runoff and improve the water quality. So let's see the design overview. So our goal is to discharging into Elk River to according to local regulation. With that, the west side of the road we use a permeable pavement shoulder, and the east side of the road we use the permeable pavement. And except that we have a dry pond, which is the detention basin, and the two covered and the ditch. The red mark shows the visitor center's water design part. So here, this page shows the details for this part. So we have a rain garden and another dry pond. For the parking lot, we use the permeable pavement, which with the grass paver. So before I introduce each designs, our design criteria are following these manuals. So now let's start for the rain garden. So the rain garden, the length is 100 feet, the width is 50 feet, and the total depth is 4.25 feet, slope is 2 to 1. With that, the capacity is 4,000 cubic feet, and the treated volume is 2,426 feet. So on the side slope, we use the grass to reduce the soil loss and control the water flow. And we use the 0.25 feet diameter pipe for the overflow and the 0.5 feet diameter pipe for the outflow. So now let's see the dry pond for the visitor center. So the length is 100 feet, the width is 50 feet, and the total depth is 2 feet, and the slope is 4.1. With that, the capacity is 7,771 cubic feet. So on the side slope and the bottom surface, we still use the grass for the same purpose. So here is another dry pond, which is the work for the road. It is the same, but had the different size. So with that, the capacity is 123,000 cubic feet. So now I will introduce the permeable pavement shoulder. So for the shoulder, we will use the porous asphalt. And the length on one side for the shoulder is 4,000 feet. And the width for one side is 10 feet. The total depth is 3.5 feet. And with that, the capacity and the treated volume is the same, which is 33,000 cubic feet. So for the gravel layers, we use 0.5 gravel Zetka to reduce the mantle loading from the stormwater. So here is the permeable pavement for the parking lots. We use the grass pavers on the ground, and we use this on each parking space. So the total depth is 4.66 feet, and the capacity and the treated volume is also the same, and that is the 14,000 cubic feet. So here we use the organized filter, and we use the 10% organized filter and 90% solid to reduce the nitrogen and the phosphorus loadings, the case by the organized filter. For the suspension layers, we use the 10% organized filter and the 60% gravel and plus the 30% the sand. And the gravel layer will be the same like the permeable pavement shoulder. So for the permeable pavement for the east side road, it is the same like the permeable pavement shoulder. And with that, the capacity is the 67,000 cubic feet, and the treated volume will be the same. So now I will introduce the culvert. So for the water resource design, we have two culverts on the east side of the road. So on the left side of the road, the culvert length is 120 feet. The diameter we use the 3.5 feet, and then the material we use the concrete. And with that, the type water velocity is 3.81 feet per second. For another one, it is the same, but the velocity is 3.36 feet per second. So finally is the ditch design. So the ditch is following the transportation criteria. With that, the total width is 21 feet, and the bottom width is 2 feet. The height is 1.25 feet, and the slope is 4 to 1. With that, the peak flow is 1.5 feet cubic feet per second. So here is the cost criteria for the water resource. The table shows all the design work, the cost, and with that, the total cost is $2,535,000. So net is for living.
Max will go.
I think it's on that black thing.
The platform for areas. This is just done with the flag. Probably were other. Configure their room. Lateral and lateral loading, which includes the rain environment, is also. Together, on the metal rack. I'm hoping. That's just because it's. Wow, larger than. But for all of this mentioned.
So I'm Barrett Church and I'm the structural engineer too for PMC engineering. So I designed a two-story multi-purpose L-shaped reinforced concrete building with an approximate area of around 35,000 square feet. It's designed for offices and academics on the first floor and residential on the second floor. And it was also requested that the roof be accessible for maintenance purposes. So just a little bit about the total work completed. First, I determined the loads for my building for each section of my building. Then I went into the beam, slab, and column dimensions. Once I had all these values, I was able to input everything into the RISA floor plan where I designed my second story floor plan and my roof floor plan. And once I finished this, I moved on to the steel selection for all my concrete elements. So my beams, my slabs, my columns, as well. I developed the lengths for all of the steel. And then finally, I completed a cost analysis for my build. So just a little bit about the design methodology. I used the ASCE 7-16 code for my load determination. So it gave me like a residential live load and a snow load given by the ASCE 7 hazard tool and so forth. And the ACI 318 code provided me with the minimum beam heights, the minimum slab heights, the beam dimensions, as well as the various code checks for the rebar selection. It also provided me with the ACI coefficient method. And the ACI coefficient method is just a way to determine the beam member moments in my beams. And I used these moments to check that RISA floor was spitting out the right values for my beams. And once this was determined, I determined that the beam member moments were less than the design strength of the members, which means that the beams won't fail in bending, which is what we as structural engineers are looking for. All right, so here are the loads, the various loads I used in my building or considered. So right there, there's a live load for 40 PSF for private rooms and corridor serving them. That is mostly for the second floor, north and west wing. Whereas the intersection is designed for 100 PSF, which is for a public room and corridor serving them. And the reason for this is just to provide accessibility for the client. Say they want a business meeting room for the residents of the second floor, they now have that option. The second floor was also designed for a dead load for the ceiling work as well as the flooring. And then the roof was designed for the snow load of 25 PSF. And not 20 PSF, which is the live roof load. And that's because the snow load's greater, which means it will control in that case. And I also added ceiling work dead load for the roof. And to the right of the table is the lateral parameters table, and that was just used to transfer RISA floor over to RISA 3D. So just a little bit about the floor plans. This is the floor plan for both the second floor and the roof. It's the same, and the beams will be the same in both floor plans. And the reason for this is just to provide less complexity for the design and less complexity for construction. And it won't, and yeah. All right, and then cross-section views. So here's a typical beam cross-section as well as my column cross-sections. The reason I have two column cross-sections is because when I transferred RISA floor over to RISA 3D, there was a torsional moment failure in some of my columns. So I had to increase the column size in some locations. So all the exterior columns are going to be 28 by 28 inch columns, whereas the interior columns are 16 by 16 inch columns, or at least most of the interior columns are. Here's just a typical beam elevation view. It shows all the reinforcement, the lap splices, the shear stirrups, the hooks, so forth. And here is a column elevation showing the same things, the lap splices, the longitudinal reinforcement, the column ties. And then the construction costs. So for my construction costs, I used RS means line item estimator for each of these things. And it spit out a number of around 2.2 million for my design. And now I'm passing it off to Emma.
So I was tasked with treating the wastewater for the proposed visitor center, factoring in 25 years of growth and a minimum flow rate of 1 million gallons per day. As you can see at the bottom, a little bit, but there's my full train of my proposed wastewater treatment. My design criteria, I use the Indiana water quality standards and a textbook I'm sure most of you are familiar with, the water and wastewater engineering textbook. The first step in the primary treatment is the partial flume. I started by using the graph there to find the minimum, average, and peak flow rates for the day, and then I took the peak flow rate just under 2,000 meters cubed per hour to find the partial flume dimensions from the table there, and you can see the partial flume. The next step is the bar rack. It will have two channels. One of the channels will be covered by stop gates. Each channel can treat the whole flow or the total flow going through each. It'll have 22 5mm bars spaced 40 millimeters apart as pictured in the bottom right. The next step is a fine screen. Of the fine screen options, there's a cafe proposed in the visitor center. So I assumed that there was going to be some fats, oils, and grease, and of the fine screen options, only 2 were suitable for that. The one with the higher capture efficiency was a step screen, so I elected to use a step screen for my fine screen. I selected the cover fine screen step screen, and it's pictured there. I selected for my grip chamber a vortex grip chamber instead of an aerated grip chamber because in a residential area, it would have a lower odors and just overall more pleasant to be around. I selected the Hubbard vortex grip chamber for max for that. The next step is the equalization basin. I use the minimum, average, and peak flow to create a graph of the flow per hour. Use that to estimate the flow at each time interval, find my volume in and out, and then eventually my max storage. The max storage plus the 25% contingency is just over 8,000 meters cubed. The last step in the primary treatment is the primary sedimentation. The flow will go into 2 clarifiers split by a splitting box. Pictured on the right side, the flow will go into the center over weirs and split into the 2 clarifiers where it will settle, and 2 scrapers at the bottom will make sure the sludge exits. The secondary treatment is a biological treatment. I selected activated sludge, completely mixed unit. The flow will go into an aeration tank that is continuously stirred. You can see the aeration tank on the top right. It will then go into a clarifier where it will settle again, and the excess sludge will be discharged, but some of the sludge will be recirculated since it is important to have enough sludge in the biological treatment. The final step in the treatment is the disinfection. I opted to use UV disinfection because it eliminates the need for chemicals, which is safer for the employees at the wastewater treatment plant and less paperwork, less operating maintenance. So overall, just a better option. I selected a Trojan UV 3000. The UV lights will sit in a channel. The water will flow on across the UV lights, be disinfected and then discharged. So my cost estimate, you can see here, when possible, I found the cost for the individual parts, but I couldn't always find costs for that. So I found projects that have been completed and used the cost of that to estimate the cost for mine. I got a total cost of $18,271,000, which brings us to the total cost of the project. It consists of the design cost and the construction cost. The design cost being $65,000, and after adding all portions of the construction cost, $28.585 million. Add them together, you get $28.65 million. It's important to note that since our project had 2 structural engineers on it, however, we were only ever planning to build one of the structural elements. We put in our cost estimate just one structural person. Just did two for the sake of a project, so. And that brings us to the end of our presentation. Any questions?
Right, can you clarify to me your statement about the snow load controls over the dead load? So you have selected one of them.
With this snow load, the 25 PSF control of the live roof load because it's used in the same.
Also live, not dead.
No.
That,
I have a question on the transportation. One is on the intersection drawing. Explain that. So tell me a little bit about what the dotted lines mean, and then also what the letters, like the cloud bubbles. Do they need-
Yeah, so I left some of the existing topography on the drawing. That's what contractors usually want to see. I've been told, but these dotted lines are my shoulders and like. You kind of see like this rounded one is the existing. Like over, and then it's like the center line, that's the existing one. Which is like the old topography.
It's like vegetation or something.
Oh, yeah, it's like trees. Get rid of those.
So. I'm not sure. Didn't mark down which slide. One more. Another one. There you go. How much is that? $600,000. What is that? It's
Miscellaneous. I don't know if to put contingency or miscellaneous, but that's
I
like,
should have gone with contingency,
Okay.
it's spelled miscellaneous wrong.
oh. Man.
And then you have a 3-lane roadway, can you go back to that?
Yeah. Yeah, 380 each approach.
Okay, so the right turns. The right turns are happen before the intersection, and you have a through and a left.
Yeah.
Okay. Exact same question, there's lots of lines on there. though.
Yeah. Little.
Good.
go back to Emma 4. Can you go back to your like cost estimate?
It's gonna take a while.
18 million for 1 million gallon. And you have 4 clarifiers. I'm looking at those.
Yes, because there's two steps where I use a clarifier and I put two for contingency on each step.
Why do you need an equalization tank? Wilson?
To make sure that my flow is always high enough and not and low enough to I don't know how to words are hard. Just to equalize the flow so that I never overwhelm my system later down the line or under my flow.
I see your logic, but do you expect that the wastewater flow coming from the visitor center will vary significantly? I'm trying to justify that in my head. Why do you need to equalize the flow?
I figured it would, just because I don't know a lot of people that go to a visitor center in the middle of the night. Plus, there is some, I think, event space in here. And during an event, the flow might be higher than
I'm just putting things in perspective. We in Balbo expanded the treatment plant by 8 million gallons and costed 12 million.
Okay.
So
Yeah,
this
these-
is 1 million gallons, so.
Yeah, so these are the numbers that I found. So I don't really know what to say.
It's fine. It's fine.
Yeah.